So we already mentioned detection and attribution. So if, for example, we detect a change in the monsoon, which we have already shown as a trend of about minus 10% over the last several decades, then you have to do an attribution exercise to see what are the causes for this trend, what are the drivers of this trend. We mentioned already indirectly that the ocean has warmed. Indian Ocean specifically is warming monotonically and rapidly, and it gets heat from the Pacific Ocean, from the Southern Ocean. It influences the heat uptake by the Pacific, resulting from the anthropogenic forcing, greenhouse gas changes, land use change, and so on. And it also affects the Atlantic meridional overturning circulation, which in turn affects the Southern Ocean and then back to the Indian Ocean, and so on. Typically, it's not very easy to do attribution from data alone, so we rely on models. Here is a good example of such an exercise. We are looking here at the historical period over which the drivers of monsoon trends have been looked at. So this is the June, July, August rainfall from 1861 to 2005 averaged over South Asia, so basically Indian subcontinent, in the CMIP 5 all forcing experiment, which means the models used in the last assessment report 5, which was released in 2014, are forced with everything we know about solar forcing, volcanic forcing, greenhouse gases from human activities, land use change, and so on. And that's the result of shown in this blue line here. And then you do sensitivity experiments where you change aerosol forcing and greenhouse gas forcing, and you try to say what the net trend is resulting from, right? So when you make all forcings, it has greenhouse gas changes, aerosol changes related to land use, land change, deforestation, urbanization, agriculture, etc., and various other drivers. So not all drivers are explicitly resolved, but nonetheless here greenhouse gas only experiment is shown in red, so you don't impose aerosol cooling, volcanic forcing, and land use change. You just change greenhouse gases, which have increased over this period that we are looking at, and the aerosol only historical experiment, which is shown in black here. Okay, so the thick lines show the multi-model ensemble means with a 21-year running mean applied. I think you know what running mean means. If you don't know, please look it up. While the pale envelope indicates the range from the mean. So you have these range from various CMIP 5 models which ran these sensitivity experiments, or attribution you can call them. So these are the various models. I'm not going to worry about mentioning them. They are all global climate models. Some of them can be called Earth system models, like the GFDL Earth system model version 2M, because it has carbon cycle, it has vegetation represented, and so on and so forth. Many of them still didn't have at that time land ice, for example, only sea ice, and so on and so forth. So all sorts of details do matter, but in this exercise we just look at the total. The curves are centered around 0 by removing the mean rainfall from pre-industrial control runs. So these models are run for a long time by imposing the pre-industrial carbon dioxide concentration of 280 ppm coming from the end of the last ice age to the pre-industrial period of, let's say, 1750 or so, and then they are integrated forward here. Units are in millimeter per day, and B is the same as A, but for global mean and the annual mean land surface temperature contrast from 1861 to 2005. So this is the temperature, and this is the June, July, August, September rainfall. The main message here, which we have to be careful about, is that we have mentioned the trend that we have been talking about, 10% decrease. The models typically don't do a good job of reproducing this trend, and when we talk in the next podcast about data uncertainties, I will mention it again. But essentially, models don't do a good job of capturing the direct and indirect effects of aerosols. And if, as we mentioned before, the relatively less warming of land in the last several decades compared to the ocean, then the land ocean thermal contrast is not captured properly, so they don't do the trend properly. But nonetheless, given their own dynamic consistency of the aerosol forcing, greenhouse gas forcing, land warming, ocean warming, and so on, you can see that the June, July, August rainfall would have been reduced even more if the greenhouse gas warming hadn't added a positive ocean land thermal contrast and increased the rainfall. So here is the net aerosol forcing alone would have put it down here, so more reduction in rainfall, whereas greenhouse gas warming has added the accelerated warming of the land we expect from its low heat capacity, which, as we said, is not realized in the real world because of aerosol forcing pollution, whereas models miss some of that. But if you explicitly include only the aerosols, they do capture the reduction better. Okay, this is the temperature. So again, here is the warming that's been observed. Aerosols overall would have cooled the temperatures, whereas greenhouse gases have added to the warming, so the net result is what we have. So this kind of attribution exercises are useful because we know what are the relative contributions of various drivers. We have mentioned direct and indirect effects of aerosols several times. I've also said what they are, but here is a nice schematic showing that the direct effects are where the aerosols are either absorbing the incoming shortwave radiation or they're scattering. So black carbon would absorb it, sulfate aerosols would scatter it, and that would change the energy budget. And those are pretty well captured by the models if they represent the aerosols in some form or the other. But the indirect effects are much more harder. Those are the ones we mentioned as the microphysics impacts, droplet sizes, cloud microphysics. There are also impacts on hurricanes and so on and so forth. And there are also cloud optical property thickness changes where cloud reflection properties can be changed by aerosols as well. Again, complicated topic, and we are just doing it very briefly here, but this is a primer to give you just a sense of the kind of complexities that are involved. Given all these things, there are still attempts to make future projections. So this is talking about the future projections. Under the future RCP 8.5 pathway, which is the business as usual pathway, 8.5 is the energy imbalance of 8.5 watts per meter squared by 2100. Following aerosol emission controls, we would expect a warmer and wetter climate over the Asian monsoon region because land would warm more compared to the fixed 2005 aerosol scenario. So aerosol loading at 2005 would be higher than what we want to do in the future. So these are scenarios into the future, so keep that in mind. Consequently, the drying trend of the Asian monsoon during the historical period will be alleviated. We'll come back to this to see the observational uncertainties in this. Also, the recently observed southern flood northern drought pattern over eastern China will tend to reduce. So the overall changes are because of anthropogenic forcing, equator to pole temperature gradient change, the energy transport required to be changed in response to that, and the changes in the ITCZ and so on will result, are expected to result in something called southern flood, so more rainfall over the southern part, and northern drought pattern over eastern China will tend to reduce. This is the projection. Okay, aerosol mitigation will lead to more severe precipitation extremes, so the indirect effects and direct effects in general would are expected to produce more severe precipitation extremes by the scaling laws we used in terms of vertical motion, saturation vapor pressure changes, and the dynamics W, the vertical velocity. So the aerosol mitigation will also include an increased likelihood of heavy precipitation related to disasters during summertime over both South Asia and East Asia, more heavy precipitation days, more extreme precipitation, and lengthier periods of consecutive wet days. There is a shift in the probability density function of precipitation extremes toward higher values over land by 2081 to 2100 over the East Asian part in particular. But again, take these with a grain of salt, because these models have uncertainties, and observations to understand the processes and to improve the models also have limitations, as we will see in the next podcast. Aerosols induce much stronger responses in extreme precipitation indices compared to greenhouse gases for the same amount of local surface warming. So if you take the warming caused by aerosols versus greenhouse gases and look at their impact, or at the climate response to those changes by aerosols versus greenhouse gases in terms of extreme precipitation indices, then aerosols would have a much stronger response, almost double the effect, as also pointed out by related studies. We speculate that this is due to the higher aerosol efficiency than greenhouse gases in modulating solar radiation, direct effects, and also indirect effects by cloud optical properties, surface energy fluxes, and cloud microphysics and dynamics, and hence induce stronger hydrological responses as seen in extreme precipitation. Furthermore, the ratios between aerosol and greenhouse gas induced percentage changes of precipitation indices against local warming are larger over East Asia than South Asia. Again, just remember these are model results. Aerosols generate a large response not only over the emission regions but also far away. So there are remote impacts. A representative example is over southern East Asia, where precipitation increases while aerosol reductions are more limited to the northern East Asia. So there are regional contrasts. So when you include the climate feedbacks, you get these regional feedbacks which produce these precipitation patterns. The aerosol-induced imprint on precipitation changes appear to be mediated by different mechanisms over East Asia and South Asia, while aerosol radiation cloud interactions are the major contributor to the response of East Asia. Atmospheric circulation changes dominate the response over South Asia. So the processes, as inferred from the models over East Asia and South Asia, are very different in response to aerosols. Okay, so this is one of those cases where aerosols, our understanding is improving, but remembering the scale at which aerosols work and the difficulty of the models to explicitly represent those scales, there are always going to be limitations. So it's going to be about understanding the uncertainties of the results. But data limitations will show us that even when the understanding is improved, the uncertainty is not necessarily reduced. So this remains a big issue. Okay, so we will leave it at that, just to say that attribution of causes for precipitation changes are quite complicated. Much easier for temperature, as always, in terms of spatio-temporal scales of temperature versus precipitation, and total precipitation versus extreme precipitation. So just keep reminding yourself of the complexities of data limitations, model limitations, process understanding limitations, and even improved process understanding limitations in terms of representing them in the models, especially for future projections. This is what we have to deal with. Okay.